In this video, I'd like to give you an overview of convection and a little bit of additional detail about how convection actually operates and some of the calculations that you can do for convection inside a building. Convection is a type of heat transfer associated with the bulk transport of particles in a gas or a liquid. Practically, in building systems, a gas would be air in a room or outside of a room, and it's either forced or natural convection. Forced convection is when a fluid movement is caused by a fan or a pump or some other mechanical device. Natural convection is associated with fluid movement caused by a temperature gradient and gravity in a fluid. Fundamentally, this turns into a density gradient that causes the air or a fluid to actually start to rotate or swirl on its own. The easy way to think about natural convection is hot air rises, and that causes the room air to move around. We have one really important equation that helps us understand both natural and forced convection. It's called Newton's law of cooling, and it's of course named after Newton. The simple form of Newton's law of cooling is that the convection heat transfer is equal to the heat transfer coefficient times the area times the change in temperature. Let's dive into each of these terms separately. First, let's look at Q. This is the convection heat transfer or heat rate. Most of the time, we want to calculate this with the unit of watts. H is the heat transfer coefficient, and the typical units are watts per meter squared Kelvin, although of course you can use English units as well. And the heat transfer coefficient is basically the way we characterize what's happening in the fluid. We often calculate this from empirical correlations or it's estimated. The area is given in units of meters squared. Areas can be tricky. It depends on what surface you have that is interacting between the fluid and the solid. So it can change quite a bit depending on the geometry of the system you're looking at. The last term is the temperature difference. This can be in any units of temperature, but we like to use Kelvin in the metric system or Fahrenheit in the English system. Often, for a convection system, the temperature difference is just the difference between the surface temperature and the temperature of the fluid. So surface temperature, T sub S, and T infinity was the bulk fluid temperature. And of course, the temperature delta is based on whichever of these is warmer, because that controls which direction the heat transfer is going. Newton's law of cooling gives us a lot of insight about convection systems. It allows us to do a lot of interesting calculations and also to quantify different systems. There's a couple of things about it that can be tricky. The temperature difference is often relatively straightforward. We can measure temperature relatively easily with a thermocouple or a thermistor or another type of temperature device. Oftentimes we can estimate the area either from a schematic or a drawing of the building system, but the heat transfer coefficient can be involved and requires us to really understand what's happening inside the fluid. Because the heat transfer coefficient is typically tricky to calculate, there's a few rules of thumb that we may want to keep in mind. The first is that for natural convection in air, we would expect a range of relatively low heat transfer coefficients. So we would expect a value of around 2 to 25 watts per meter squared Kelvin. For forced convection, we expect a much larger H, 25 to maybe 250 watts per meter squared Kelvin. Now that's just for air. In liquids, it can vary in a different way. You can get slightly more precise estimates for heat transfer coefficient using a heat transfer textbook or the ASHRAE handbook. The reason the heat transfer coefficient varies so much is because it's capturing different properties of the fluid behavior. And there's a couple of things that we need to understand to really unpack that statement. Let's think about an example for a building system where we would expect convection to occur in lots of different ways and in lots of different flow regions. A window is a great example. We would expect the air outside of the window to be driven primarily with wind and other things that cause a pretty steady or higher velocity. So this would typically be considered forced convection. The second type of airflow to think about is what's happening inside the room. So inside, you might have a couple of things happening. You could have a fan blowing, which would cause forced convection, or if you don't have very much airflow in the room, you might actually have natural convection. You might think we're finished thinking about convection for this window, but there's actually one additional type of convection, which is between the two panes of glass. You actually oftentimes have an air gap or some sort of a gas trapped between double pane windows. And inside there, you can also have air movement. The interesting thing about convection inside a double pane window is the manufacturers will have designed things like the geometry, the gap between the panes, to optimize the system and typically keep the convection relatively low. So this could be natural convection, but it's probably going to be a pretty small h. So that helps us calibrate to the different heat transfer coefficients. We would expect a really small h inside, maybe like 2 or less, inside the two panes of glass. On the outside, for the wind, we'd expect to have a relatively large heat transfer coefficient. And inside the room, depending on whether we have forced or natural convection, we'd expect it to be somewhere in between, maybe in the range of 25 to 50, depending on what's happening in that room. So of course, this doesn't give us actual numbers we can use yet, but it does help us think about what's happening for the system. The first type of fluid behavior that we define is called laminar flow. We associate laminar flow with much smoother behavior, lower velocities, and typically less mixing. So if we were to draw a picture of this, we would have a flat plate or flat surface that our flow is interacting with at a specific temperature. And then we draw a laminar system as a relatively smooth airflow over the surface. The other type of behavior that we will talk about is turbulent. Turbulent behavior is much more chaotic. It tends to include a lot of mixing and a lot of fluid motion as eddies. So we oftentimes draw turbulent flow as rougher with lots of swirling behavior. Now you might have noticed that I drew both the laminar region and the turbulence region on the same surface. Oftentimes, with different flow parameters, we would start out laminar initially, and then we will transition to turbulent. When and how these transitions occur is actually a huge part of how we actually determine the heat transfer coefficient for a system. And the line I've drawn here that represents the different regions is what's called the boundary layer. And that boundary layer is the way we distinguish sort of what would happen in these different regions. So how will we know what flow region we might be in? Often we use dimensionless numbers and very specific information about a fluid to answer that question. So we have a couple of different calculations we can do that help us understand this. The first dimensionless number is the Reynolds number. The Reynolds number is the ratio of inertial and viscous forces. And we have an equation that we can use to calculate this. So we determine the Reynolds number based on the fluid velocity times a characteristic length, which is something in the geometry, and the viscosity of the fluid, which is a fluid property that we would often look up. So in order to do this calculation, we do need to know something about the velocity of the fluid. The second dimensionless number that we want to think about is the Nusselt number. The Nusselt number is the ratio of convection to conduction in the fluid, and it's really important in convection and understanding convection flow. We can calculate the Nusselt number based on the heat transfer coefficient times the characteristic length of the system, and we divide that by the thermal conductivity of the fluid. And this helps us, along with the Reynolds number, to characterize the flow. Practically the most important reason that we have the Nusselt number is we actually use it to solve for the heat transfer coefficient. So very frequently we reverse this calculation and use the Nusselt number to determine the heat transfer coefficient because it's quite often that we're looking for H. Let's think about another common example for convection in building systems. Let's think about an air duct for a moment. Air ducts are really important because they help us move hot or cold air from our HVAC system into the conditioned space. So we need to be careful to think about the heat transfer that might be involved here. So we're going to look at the duct from the side because this will help us think a little bit more about what's happening from the fluid standpoint. We have hot air coming in from our furnace, so we'll assume it's the heating season and we have warm air coming in. What's going to happen is as we start to flow through the duct, we're going to start out with a laminar region adjacent to the surfaces of the duct. So here we would expect this entry region where we're going to have a relatively laminar flow behavior, but it's going to happen from each surface, the outside surface or the top surface and the bottom surface. And it'll start to converge, and then eventually we're going to have a transition. This transition is the fully developed region. It's the part of the flow where we have a fully developed and laminar pipe, and everything is going sort of as we would expect it. In a pipe system, we associate laminar flow behavior with a Reynolds number which is lower, typically less than 2,300. And we can use that Reynolds number to help us determine how long the entry region might be. If we define the entry region from the start of the pipe, we will call it the hydrodynamic entry length, and we'll use X, FD, H, which is X for fully developed hydrodynamic. Calculate this by just knowing the Reynolds number. So as long as we know the Reynolds number, we can figure this out, where the relationship is the hydrodynamic entry length divided by the diameter is equal to approximately 0.05 times the Reynolds number. And that'll tell you whether you're in the entry region or whether you're in the fully developed part of your pipe. It turns out we have a similar rule of thumb for a turbulent system, which is that this will occur between 10 and 60 for the ratio. Once you know the hydrodynamic entry region and whether your pipe is laminar or turbulent, you're going to be able to select the correct Nusselt correlation or experimental correlation to find the heat transfer coefficient. This is a lot of work in order to get one number, but it turns out there's a lot of complexity in the heat transfer for convection systems. If you work in this industry, don't take those duct flow calculators for granted. There's a lot going on under the hood. We spend a lot of time trying to understand the different flow behaviors because it's important for us to figure out how to get the heat transfer coefficient. If we go back to the example where we had been thinking about the different flow regions, we started out with laminar, we went through some sort of transition, and we eventually ended up in turbulent. The heat transfer coefficient changes as these different velocity and flow characteristics change. And of course, as I mentioned, this is the boundary layer. So we can add to this graph the transitions that occur with the heat transfer coefficient. So it starts out right at the edge. It's relatively smooth or even through the laminar region. And then we see a big spike up as we go through the transition into the turbulent region. And then it's going to reduce a little bit, but stay relatively high. So this is how the heat transfer coefficient changes as we change flow characteristics or flow regions. So when we go to determine all of these things, if we were going to actually do this calculation, we would start by first calculating the Reynolds number. We'd use the Reynolds number with a correlation to calculate the Nusselt correlation or the Nusselt number. And then we'd use that to calculate the heat transfer coefficient based on the definition of Nusselt. So this is sort of a shortcut. When you think about these calculations, oftentimes we go Reynolds to Nusselt to H. And then H, of course, characterizes for us the flow and what's actually happening from a heat transfer standpoint. And that allows us to put all of the pieces that we need together. So let's go back to the example we had with the duct for just a minute. Remember that we had warm air coming into the duct. But this time, let's think about this system in the context of the overall heat transfer and all the different things that are happening in the system. We learned before that there's a couple of different things we need to understand the temperatures in the system. So where are the warm temperatures, where are the cold temperatures, and what is that going to do for heat transfer? We should have the warmest temperature in our duct system near the inlet of the duct, but also near the center of the duct, because that's where we should have relatively fully developed flow behavior. The next temperature in the system is going to be right at the edge of the duct wall, but we're going to have some heat transfer across the duct wall, and then we're going to have another temperature, depending on where your duct is located, in the air outside or around the duct. If we turn this into heat transfer diagrams, which can be helpful for us to visualize this, we have heat transfer through the air in the center of the duct, and then we have, and that would be convection, and then we have conduction through the solid wall of the duct, and then we have convection again between that wall of the duct and the air around it, because that's the colder air outside in the attic or in the crawl space. There's one other form of heat transfer that we might also expect. We probably have some radiation to the attic walls or to the surroundings. We may also have radiation inside the duct, but it would be a relatively small contribution relative to the high velocity of airflow through the center of the duct. So we'll probably just leave that one off in our picture here. But it gives you a sense of the different types of heat transfer happening in the system. Now, if we wanted to characterize and calculate some of the different modes of heat transfer, we now have the tools we need to do that for convection. So if we want to do a calculation for this arrow right here, we now have a sense of the steps that we need to go through to find out exactly how much heat transfer is happening due to convection. And so the steps for that are first characterizing the flow based on the Reynolds number, then calculating the Nusselt number from a correlation, and using the definition of the Nusselt number to get the heat transfer coefficient. Once we have the heat transfer coefficient, we can then use Newton's law of cooling for the final calculation. In this calculation, as long as we know the temperature difference, so in other words, if we know approximately the temperature of the air inside the duct, which we can probably get a good feel for based on a thermostat setting and some information about our HVAC system, and then we know the temperature of the other system, which is the outside attic or crawl space temperature, we could probably estimate that pretty well based on weather conditions that we can look up. So that leaves us with the heat transfer coefficient, which we're going to have to solve as I outlined before. And then, of course, we need to know something about the area and the geometry of the duct in question. So this gives you a sense of how complicated the convection flow in a duct or in any sort of system in a building actually is. All of that complexity can make it very difficult to design buildings to be perfectly energy efficiency. But that challenge is worth it, because if we can get a better sense of how fluid flow and airflow and then in turn convection are interacting with different systems, it helps us make the home more comfortable for the occupants, and in the long run saves a lot of energy and money for the people who live there. Thank you for joining me for a conversation about convection. Convection is a complicated and rich topic that can really help you understand heat transfer inside a building system.